Like, where you always say, like, how many questions and.
You know what, just,
Like you did
a
last.
lot of multiple choice questions. Yeah, maybe a couple of drawings.
Anything stuck with you?
But obviously, you're going to need to know how to do the valence bond.
Molecular orbital as well.
Well, valence bond. Let's talk about that. You're going to need to know how to draw the atomic orbitals. Whether they're hybridized or unhybridized. Right? But you're going to have to be able to do the orbital overlaps. You have to know, what is a valence bond? What is a valence bond?
Is the overlap of the orbital?
Which causes what? I mean, well, how does a valence bond bond?
Like the overlap of the orbital.
Not
Hybridized the orbital?
the overlap of the orbitals does what?
It minimizes the orbital.
The nuclei are attracted to the electron.
Yes, that's it. Or electrical. There's got to be electrical attraction. It's not just orbital overlap. Like it creates a greater electron cloud density, which causes because we got to talk. The orbital overlap does not hold the atoms together. The electrical attraction
What happens when they
hold together. How does it differ from molecular orbital?
molecular orbital, they fuse, like they combine.
No. How does a bond, let's say, a bond compare? I mean, how are the atoms held together in molecular orbital theory? That's this.
The atoms form new orbitals which the electrons occupy.
That doesn't really tell me how it's held together, because it's more complex than that.
Isn't it multiple fractions?
The most important things is a bond holds the atoms together, and so you should know how a bond works. And so how does a bond work in valence bond theory? How does a bond work in electrical attractions again in molecular orbital? But a little different explanation. What do we say in molecular orbital?
Do they
Because-
one?
Yeah, they do. They form molecular orbitals. But the problem is you can't just say they form this, because they also form that, which is what. Right, and so it doesn't work just saying this and ignoring the other thing and saying, well, the other thing, we can ignore it, it doesn't exist, right? You have to explain it, and so to explain it to me. And I said it before, I said it multiple times. Yes, that's exactly it. Greater bonding electron density than anti-bonding. So if you have more bonding electron density, you're going to have net negative charge in the internuclear region, which is going to hold the atoms together.
So greater bonding than.
This whole thing is discussing where the electron density is, the whole valence bond and the molecular orbital. And we need to know that for bonding, of course, but it's also a key for certain other properties as well. We'll talk about.
So greater bonding than anti-bonding.
Yes, exactly. And having greater bond, how does having greater bonding? Because having greater bonding puts electron density in the, whereas antibonding orbitals have a node in the internuclear region, right? All right, so you have to draw, all the valence bond stuff we did with the energy level, orbital energy level diagrams and that kind of thing. You have to be able to do that.
We have to go
You should be able to do a multiple bond. It should be easy to do like a double bond. That should be something simple than a triple bond, yeah. A PD bond you aren't going to have. Yeah, Matthew?
In valence bond theory, the bond they're not attracted to each other's nucleus, they're attracted to the overlap of the electrons. So like when the orbitals overlap and they create a greater, that's what the nucleus is actually being
Yeah,
attracted to,
right.
So it's not the.
It's a balance, actually, when you think about, even in valence bond, there's a balance, because having the orbital overlap creates a higher probability density in that region. And so it's a balance between the attractions and the repulsions. And it turns out the attractions win over the repulsions when that happens, because the nuclei are going to repel each other.
So like on the one test, exam 13, for in valence bond theory, a bond consists is the overlap of atomic orbitals, isn't it? It's not the direct attraction between nucleus A and nucleus B. There's no direct attraction between the nuclei.
No, there isn't. Right. Yeah, so in simple terms, people memorize this. The people memorize that valence bond is the overlap of atomic orbitals. Molecular orbital is the linear combination of atomic orbitals to form new orbitals called molecular orbitals. Right. And then the bond, what is the force that holds the bond together? That's actually the same in both, it's electrical forces.
Professor,
Uh-huh.
did you say we're not gonna have to draw P?
You're not going to have to draw what?
Was that what you said? I didn't catch that.
No, it should be easy to draw PP.
Oh, yeah.
It should be easy to draw that.
But then you said we're not gonna have to draw.
PD, PD,
Okay.
what we talked about yesterday.
And then I have another question.
But are we gonna have to draw any molecular orbital energy diagram?
Yes, you should know the molecular orbital energy level diagram.
Professor?
The molecular orbitals, let me just finish this. So we got the less than 8 and then 8 or greater. And so less than 8, you just remember the pattern. It's a 1, 1,
That's an 8?
2, 1, 2, 2, 1. I don't know the easiest way to remember it, but these come from the sigma 2s, these come from the sigma 2 pi 2p MOs here.
What is 8? Is that?
8 is up. The number Z.
Z.
And Z.
Over a
The
proton.
atomic.
Yeah.
Just
1, 1, 1, 2, 2, 1. And so what you remember is this, 8 has this symmetry, 1, 2, 2, 1, and then these two here. Less than 8 is this pattern here. There's a difference in this is the same in both. It's just, so some people make drawings or something, two triangles.
For Z, do you take the addition of the Z for the two atoms, or is it just
No.
the small time?
No, Z for, these are homonuclear. Homonuclear, the Z has the same, right? Heteronuclear is different.
We use less than 7.
So you use less than 7 for heteronuclear, right? So the Z is the same. N2, no, you don't add it. N2, the Z is 7. O2, Z is 8. Yeah. CO, well, Z is 4 and Z is 8. Or 6 and 8, sorry. Z is,
Can you use the lower one?
yeah, we're going to use the lower one, given that condition. All right, what was your question?
Professor, when you were talking in lecture about bond length and bond energy, you said that sigma bond is longer and weaker, and that the double bond is shorter and stronger. Single bond, not sigma bond. Single bond is longer and weaker. Double bond is shorter and stronger. Triple bond is shortest and strongest. But then in lecture, you said something about single bond, and then after that, like you talk about single bond like being sigma bond.
Yes,
But even a sigma bond is stronger than pi bond?
yes, right. sigma bond is stronger than pi bond, but a double bond consists of 1 sigma and 1 pi. A triple bond consists of 1 sigma and 2 pi. And so sigma bonds occur in single, double, and triple bonds. The only difference is the additional pi. And so the point I was trying to make there is, does the bond energy double with a double bond, or triple with a triple bond? No, it doesn't, because it's pi bonding. It's not as strong.
And then the sigma bond can rotate, but...
Rotate freely without breaking anything. You know, if you rotate it, you don't break the overlap. And it's, the pi bond, you break the overlap if you try to rotate. But you know, the p orbitals are like this, they have to be lined up. If you try to rotate this atom, you got to break it. And so it's called free rotation. So, and this happens for molecules. Let's see. So I have this out here. This is, well, actually, I'm going to go to, I want to see a big molecule here, but not too big. So you can see some rotation. Maybe this might show some rotation here. Maybe this one will do it. Do you see? This is called rotation here. You got free rotation. Do you see how it can rotate?
Wow.
These parts are rotating. Whereas if you have a double bond in there, it's fixed. It's going to be very rigid and it won't rotate. Like there's probably a double bond here. Do you see? This looks like sp2, and so that looks like it's not rotating at all. And so there are going to be parts of the molecule that rotate, parts that don't rotate. You know, in this. Let's see if this is. Yeah, you can see there's going to be rotation. Do you see how this kind of moves? Although it's all interconnected. These are molecules are too big. This is a protein molecule here. Oh, okay, but this is too big. Yeah, it's important in when you're thinking about certain things. Let's see if we can see something a little bit better. Sound is on. Oh, this is important here. Do you know what they're showing? This is what we can see in Spartan.
Polar.
Yeah, polar, non-polar. You know the red, you know what the red indicates?
Electron.
Negative charge density. The blue indicates positive charge density. And so this is what we want. We want the kind of electron density map, and then we want to see how it's kind of polarized like this. We could do it using oxidation states. We could do it with formal charge. This is water, I think. We could do it with formal charge. Formal charge doesn't tell us anything. 2 hydrogens are 0, oxygen 0. Oxidation states tell us oxygen's -2. And the reality is it's between formal charge and oxidation state because those are the two extremes. Formal charge assumes pure covalent, oxidation state assumes pure ionic, water's neither. And so this is gonna be like, I think the charge on oxygen is like minus 0.9, you know, not minus 2 oxidation state, not 0 like formal charge. But that's important because it tells us, you know, because chemistry is all electrical interactions, it tells us a lot about the electrical interactions here. Minus 0.8. And hydrogens are plus 0.4. This stuff we can get from Spartan. These are vibrations. We talked about vibrations earlier. Vibrations are actually quantized. And so water cannot vibrate at any, this is a vibrational band here. And so this is vibrational rotational band. So we can see. This is molecular diagram. Sometimes we look at individual molecules. Individual molecules in a vacuum is easy. Then you start adding other molecules, and you add one other molecule, the calculation becomes much more intense. Then you add a whole bunch of molecules, and the calculation becomes much more intense, and you have to do, you know, approximations here. So this is molecular dynamics. You can see the bar molecules rotating. They're all stuck together, right? Why are they stuck together? Is it because of gravity? No, they form a sphere like this. It's electrical attractions. In fact, we're going to talk about these electrical attractions today. They're stuck together primarily because of hydrogen bonding interactions. This is a spectrum here. You know, oh, molecular dynamic simulation is black and the red is experimental. There's pretty good agreement, it looks to be. I don't know what temperature this is. This is rigid. Do you see any rotation? You know that this is benzene. It looks like, well, no, maybe it's not benzene because of the nitrogen right here. You see the blue is nitrogen. Maybe this isn't what I want. I wanted to show some rotation of some bigger molecules. There's a molecule that's vaporizing off the surface, escaping. This shows some more. If you see these long chains here can rotate with this. Oh, I know what we need to show. Three molar aqueous potassium carbonate. VIGO. So a lot of people do this because, you know, proteins, they're moving around, right? And how does that affect their, you know, properties? And so people, what they do is they freeze the protein into a crystal lattice and then measure, you know, the bond angles and everything else. But that's not reality. Reality is this protein's continually moving about, vibrating, rotating, doing all this other stuff. This is some kind of anti-tumor agent, maybe. These are drugs. This is DNA. They're looking at how things might bind. This is another protein. Sometimes the structures, they form these ribbons, sheets of atoms. Let's see, molecular dynamics animation of let's try another one. Lipids are fats. So lipids, that you have unsaturated fats, which are all sp3 carbons, and then you have saturated fats, which have sp2 carbons in their double bonds. And so this would be an example of saturated. With this one has wait, did I get that right? Sorry, let me just it up. Saturated has all sp3. Sorry, and so it's like this, and then this thing can undergo free rotation. Unsaturated would have a sp2. Sorry, I got that backwards. And so do you see it's rigid where the double bond is? The double bond, it can't rotate there. But otherwise, it's floppy everywhere else. You know, that affects its state. You know, having that kink in there means it's harder to pack together versus these. These are totally unkinked. And this kink comes from having that double bond in there. And, you know, let's see.
Yeah.
This is at, you see this one melts at a much lower temperature. This one's going to melt at a much higher temperature. Let's see. Yeah, 70 degrees, this one starts to melt. Melting, you know what melting is? You just break them apart so that they're free to move and translate. Let's see if this has more. This is just looping. Oh no, here's not. Maybe this is going to show more. So saturated here means saturated in terms of hydrogen content. You know, the maximum amount of hydrogen can get in there. So you got this kink from the 120 angles, double bond. That wasn't, that was more cartoon animation. I was looking for a real simulation. Let me add that in here. Well, this doesn't, but here you see there's no rotation around here. It's going to be sp2. Those are sp2 carbons, by the way. They don't show the hydrogens here for clarity. Okay, this doesn't really have any dynamics. Oh, this does have some dynamics. Here we go. Do you see how these parts can flop around because there's rotation? But at the double bond, I don't know, are there any double bonds? Do you see how everything's kind of rotating? Because those are sigma bonds. We can have free rotation about the sigma bond. This is molecular dynamics computer simulation. This is stuff you could do on Spartan too. With the interaction. All right, that's enough. There. Okay, here. This is in organic chemistry. You do a lot of this. You look. They call these the conformations. This is the energy of the conformation. You know, the barrier to rotating a bond. You know, if you have to break the bond, pi bond or not. All this structural stuff plays a role in the properties. That's why people care about, you know, what position it's in. But when we draw these things, we just try to draw them in the simplest conformation. Here. So for example, this thing here, you know, we just try to draw it, put as many atoms in the plane, you know, But that's not necessarily how the structure is going to be, because, you know, it can rotate out of the plane, do a few other things, but, you know, one instant of time we can capture in the plane. And we just draw it, so it's easiest to draw. All right, other questions?
So for molecular orbitals, you would have to draw a diagram,
Yes, this one. You have to label it too.
right? Label.
Yeah. Yes.
For filling up the electron for the MO theory for
Mhm.
oxygen, O2,
Yes.
well, there's 12 electrons, but just basically filling out all from second period. What about the first period?
First period are there. So this is something you have to watch out for, because there are two ways of counting O2's electrons. The total number of electrons is what? 16 in O2. The total number of valence electrons is, and so if you look at all MOs, then there's the sigma 1s, sigma star 1s. And then the sigma 2s, sigma star 2s. Now this is Z, O2 is Z, yeah, and so we do this, we do this pattern, the symmetric pattern, sigma 2p, the pi stars, and the sigma star, 2p's, right? And so here, we do 16 electrons here. Here, we would do 12 electrons, because we're only doing the valence versus all. But we're going to get the exact same diagram. 2, 4, 6, 7, 8, 9, 10, 11, 12. Over here with 16,
We're just ignoring the core electrons, right?
yes. So you have to be careful, because you know what happens on the test? People will use the valence MOs and count 16 electrons. Or people will use all the MOs and count 12 electrons. And so they get, it's easy to get mixed up. In fact, I did it myself when I was covering MOs. I remember it got mixed up. All right, what else?
So,
Oh, just a second. Hold on. What was
You
it?
say all or valence, right? You can tell us which one.
No, you do the valence.
The valence.
Because that's what the book does. The book does valence. The book doesn't do all. Other books do all, which is fine, but
ignore the core electrons, right?
the core electrons aren't going to participate in the bonding anyway. The core electrons,
It's just there.
bonding and anti-bonding, and so they don't really participate in the bonding. It's the valence electrons that participate in the bonding. Yeah, that's tricky because, like in Chem, let's say you're in Chem 1A, you're doing it this way, and then all of a sudden in some other class, they do all MOs. And you're used to doing it just the valence. Then you get tripped up. So we'll just be consistent with this time. All right, what else?
About how many, like, chemical traces?
I don't know, about the same as last test. I haven't, something like that, yeah, 40, maybe less. Yeah, quite a few multiple choice, and then a couple of drawings. The valence bond, no, you're going to have a valence bond drawing, right? I mean, you already predicted that, I hope. Right? And you're going to have an MO diagram drawing, right?
Yeah.
And those things are given. Although, I don't know, you know, yeah, those things are pretty well given. For valence bond, you got to do the whole Lewis structure, right? And you got to know the geometry, the shapes, that kind of stuff. Do you know the molecular geometry? Somebody asked me yesterday, do we need to know the molecular geometry? You should have been able to predict that. No, I know. I'm
You
just,
said something about the chart, like you were
Yeah.
reading the chart or something.
yes, you definitely need to know, except some of them, like SP3D and SP3D2, because there's some controversy regarding that. That's a bit trickier. And so if you're given something like this, PCl5,
So remember,
you would just do it as you normally do it. Remember when we were talking about this might not be all covalent like this? There could be a significant ionic contribution. Don't worry about that. Just do it as you normally do it. You know, this one. Is this octahedral? Trigonal bipyramidal. It is not octahedral. What does octahedral look like?
one more square.
Yeah. Why do they call it octahedral if there are only 6 things? 8 faces to the octahedron. So if you connect it, you form an 8-sided polygon. You connect the 6. Yes.
And for something like that, would we have to know how to do the valence bond?
Yeah. When I ask you a question about the valence bond, it's going to be, what is the hybridization? What is the hybridization? SP3D. If you look at the practice exams, I'll give you some kind of Lewis structure and ask you, what is the hybridization of the central atoms? That's it. And so that means you're going to have to be able to draw the Lewis structure and then figure out the hybridization. I'll ask you, in addition to that, I'm going to ask you, what is the molecular geometry? Probably like on a multiple choice style question, you know, where I give you the structure and you'll have to figure it out just by drawing it. But I'm not going to grade your particular drawing. I'm going to primarily look at your valence bond drawing, you know, to see, you know, how you're drawing the orbitals. For example, if I see sp3 orbitals like this, there's a problem with this. What's the problem with this? Yeah, because the problem is I think this is trigonal planar. This trigonal planar arrangement here, because all 3 look exactly the same to me. So it's trigonal planar. Yeah, so make sure you shade one. And you know, if you could just draw this kind of similar, like this, or get in the habit of, there's 2 in the plane this side and 1 in, 1 out on this side. Some people do this on the test. They'll shade this one. But then I think this is kind of a weird geometry. Yeah. Because one of the one of the tripod legs has been distorted out of place. It looks like it has a broken leg. Because normally it's like this, you know. It's a tetrahedral kind of looks like a tripod, but this one's been twisted back. And so it looks a little funny.
You draw a water molecule. They have 2 electrons, 2 lone pair electrons.
Yeah.
They're sticking up.
Yeah.
If you draw dash and wedge and then attach like electron, is that wrong? Or is that
Well, if you were to draw water like this, it's not like, let's say you mean like this? Is that what you're saying?
Yeah, like, there's a hydrogen this side, and wedge and dash. Then you draw wedge and dash, and then draw electron on the dash.
Okay, wedge and dash, and draw the electrons where?
On the dash and dash.
Like this?
Yeah, is it wrong?
Some people will say this is wrong. Do you know why some people will say this is wrong? They'll say this is wrong because a wedge and a dash represent 2 electrons. And so some people will say this is wrong because this is 4 electrons, 2 lone pairs. Other people will say, no, it's no big deal because everybody's going to recognize that it can't, if you draw like this can't represent the electrons. It's got to represent the electron pair coming out, right? And so, to avoid this debate, I just draw it like this. So I have 3 ways to draw the lone pair. I call this one in the plane, this one's coming out, this one's going.
What was it again? In plane?
In the plane, coming out, and going in. But, you know, if you use the wedge like this and a dash like this, I will not mark it wrong.
Do one.
Yes.
Sorry, can you see a molecule with a pi bond seen to the side? Like,
A pi bond side view?
yeah.
Anyone in particular?
No, seen to the side. Like, I've seen you draw it from the top a lot, but,
Well, let's do this one then. In this case, for the oxygen, we don't really have to worry about showing the 2 electrons coming out because the orbital's already coming out here. The orbital's already going in there. And so there we don't really have to do anything extra.
Is this formaldehyde?
This is formaldehyde. I picked formaldehyde because it's one of the easier ones. So that would be the PP pi bond. So you have to draw like that. Well, we did a triple bond yesterday, but you know, with the triple bond, what was the triple bond we did yesterday? Carbon monoxide? With a triple bond, you don't have to show me a top view and a side view, right? Because it would look exactly the same. So you would just show me one view. The triple bond had another p orbital sticking out and going in, and sticking out and going in, and just p there, like this. That was the triple bond. Carbon monoxide. That one is easy also to draw, right? The other side, do that. What was the hybridization on carbon monoxide? SP. So we have our SP sigma bond.
We have going up and down and electron.
Yeah, so this pi bond would be shown side view, but we'd also have a pi bond shown top view on this very same molecule, which would be where? Yeah.
They look the same.
So we got the 2 PP pi bonds. Label it, right? Everything.
How do you want us to do the SP and the P? Show the hybridized and unhybridized?
Yeah. I need you to do that for carbon, SP. So you need to know this pattern.
That's why I
double bond.
Yeah, you have one lone pair, and then a triple bond to oxygen, or triple bond to oxygen. SP here, a P here, a P here.
It would be the same oxygen.
Yeah, it's the same oxygen. There's only one oxygen here, so here, here, and here. It's a triple bond. So can you do that?
Yeah.
Can you do the same thing for oxygen? Can you draw it? Can you label the orbitals? Can you label the bonds?
SP sigma bond, EP pi bond, EP pi.
Yeah.
Then you'll be all right. Can you do the MO for this? Yeah, carbon monoxide.
That would be like both valence electrons with both elements together.
Yeah, right. Which diagram would you use for
Less
that?
than seven.
Less than seven. When you count up the electrons, 4 electrons for carbon, 6 electrons for oxygen, gives us 10 electrons total. And they fill up the diagram. Can you figure out if it's diamagnetic or paramagnetic? In both valence bond and MO? Yeah, good.
For oxygen, we fell.
Yeah.
Yeah, oxygen, they conflict. Which one is correct? You should have it memorized. Which one. Yeah, right. Actually, oxygen is probably pretty easy to do too. You know, oxygen you'd show a top view and a side view.
When I look at the casper for MO
Yeah.
or CO, the number of orbitals looks differently than the way you did it. It goes up to like a 4 something, like 4 times, like 4 6.
Pair equals pair.
Yeah.
They're the same. This is the one in the P orbital is just right. So it goes
Spin up, spin down.
just
Half the ground.
It's like
Oh, this is so slow.
very net.
Okay, I don't know why they did this, but they do, there are different ways of numbering or labeling the orbitals. Right, so this is the sigma number 1, sigma number 2, sigma number 3, sigma number 4. And then they did the pi's, you know, here. Pi 1s, pi 2s. But you would know sigma number 1 is actually a sigma 2s. But there's additional, you know, it's not just an LCAO of the 2s. There's additional mixing. Do you see the additional mixing? Take a look at the dash line and then you can see maybe some additional mixing. Actually, there's not really much here. This should just be a sigma 2s, right? And then this should be a sigma star 2s. Sigma star 2s. But if you look at there's some 2p mixed in there. You see that? And so this is getting more complicated because there's additional mixing of the waves. Have you ever seen, like sound waves? How they're mixed, and they're convoluted and deconvoluted? You know,
That video shows with the sand.
yeah, with the sand. You listen to the music. Actually, that was. Couldn't hear the music. They have.
This song shows they would form the weakness.
All right.
Sound waves. That, they could cancel each other out, or they could simplify, or make a shape. Waves make orbitals, like
Actually, is the sound's not working here, is it?
No, just.
Oh, I know what the problem might be. I don't know if this is worth showing. But the point is that there's additional mixing that goes on. You know, even the bond angles aren't always the, let's say if you have a bond angle that's, it's supposed to be 109, but it comes out more like 104, you know? That means there's a lot more P character in there than S. And the closer it gets to 90, the more P character there is. And so we could calculate the percentage P character roughly based on the angle. If the angle is 109, then we know it's 75% P character because that's SP3. If the angle is 90, then it's 100% P character. And so we can just figure out based on the angle how much P character got mixed into that molecular orbital. That kind of thing. So let's see.
That's all I hear.
All right, this is not working. Forget. I mean, you can check it out on yourself. But this is a whole bunch of different frequencies mixed, right? Into this. So what we're looking at here is they don't label like we did because there's additional mixing. And because of that additional mixing, you shouldn't use it, and saying that this just comes from the two S's because there's some 2P in there too. And so but for us, you know, the diagram is like this. Sigma 2S, sigma star 2S, pi 2P, sigma 2P, pi star 2P, sigma star. This is the same pattern, exact same pattern, you just put in the labels. So you already have it memorized, right? So just do that. Or I don't know if you have it memorized. Do you have it memorized? Okay. All right. What else?
What's LCAO?
Linear. This is the dashed line. We're combining two atomic orbitals to form two molecular orbitals.
That's what it is.
That's all it is. LCAO is the quantum mechanical term here.
There's two of them.
The LCAO is talked about when we're doing the 1S's here. This is the LCAO. Linear combination of two atomic orbitals to form two molecular orbitals. Okay. That's all you need to know. What else?
Question for this problem. Model exam.
Okay, just read it out.
Which species the most basic?
Which what?
Which species is the most basic?
Okay, which species is the most basic? I skipped that. I skipped it because, you know, this is at the end of chapter 9. Metal oxides are what we call basic, like calcium oxide.
So it's calcium oxide.
Non-metal oxides are acidic. This is Lewis. Acidic like a CO2 example. Semi-metal oxides are amphoteric. You can go either way. Example, Aluminum oxide. Aluminum, though, most people consider metal. But something like, germanium, arsenic, silicon, you'd expect those to be amphoteric. They can go either way because they're borderline. So they have properties of both. And so aluminum oxide is technically, aluminum oxide should be able to react with acids and it should be able to react with bases. And it does, but it's very unreactive. Aluminum oxide is very stable. Can you tell me why you might think aluminum oxide is very stable? Let's consider ionic, because typically we think of aluminum oxide as being an ionic compound, right? Aluminum ion and oxide ion. Why would aluminum oxide be so unreactive? Aluminum oxide is what they call alumina in the ceramic world, and they use it for lots of things. They make alumina cookware. Alumina cookware can withstand extreme temperatures metals couldn't handle. And so you use alumina pot, which is just this white ceramic pot, and you can heat up to like 1,000 degrees without it vaporizing. You put metal in there and it starts to vaporize everything.
So why is it stable?
Yeah, why is it so stable?
Bonded for this one?
High charge, right. Aluminum is 3+, oxide is 2-. That's going to be a strong ionic bond. Very strong ionic bond. So it has extremely high melting point. Aluminum oxide is what aluminum is made out of, right? This occurs as an ore, bauxite, and bauxite is very common. You find these in tropical islands, stuff like that. So there's lots of bauxite ore, but it's very hard to extract the aluminum out of there because aluminum oxide is so unreactive because of that incredibly strong bond. This is why the guy who figured it out became. They said, I think there's an interesting documentary if they're ever interested in it. He became like one of the world's richest men at the time, turn of the century, figuring it out.
It's in a lot of things, right? I guess like in deodorant and stuff like that too, right?
Aluminum oxide? Aluminum oxide is used for so many things.
Yeah.
It's a very tough material also. So for nuclear bomber pilots, they make their goggles out of aluminum oxide, and they dope impurities in there so that when electric voltage is applied, it blacks it out completely so you can't see through it. So single crystals are transparent. And so like if you look at salt crystals, you can see through them, but when you look at a whole bunch of polycrystalline materials, they don't look so transparent. But a single crystal aluminum oxide you can totally see through, but most aluminum oxide materials are polycrystalline and then sintered together, so the crystals are fused together. You can see through it. And so those are the electrochromic things. They have ones that I guess are, they look for other applications for this type of stuff too. What were we talking about?
Linear combination of atomic
Linear combinations of atomic orbitals. This question. So the answer is calcium oxide is the most metallic of them. The most metallic is going to be basic.
It would be calcium oxide.
Calcium oxide, right. Which one's the most acidic? CO2 is the most acidic, right?
That's what happened in the experiment yesterday.
Yeah, right. Water gets contaminated with CO2.
What about the transitional? Did they do?
Transitional oxides are basic. Yeah. So what else?
The C effective for iron exposes to what? Number 13. It's SAM11.
Well, Z effective is, just a simple way to calculate Z effective is take Z minus the number of core or inner shell electrons. And so iron has how many core electrons?
Iron. And B.
18?
Yeah, it has, it's a transition.
Yeah, 18, right?
Multiple.
More than that.
Yes. So 18 minus.
22? Counting 22. Counting 22.
What's auto?
It's not counting D over there.
Z is 26.
Use some periodic table here.
It would be 26 minus 18.
Probably the easier thing to do is just do this. A lot of people will say 18 core electrons, but maybe we shouldn't say core, we should say inner shell electrons, because inner shell electrons shield the outer shell electrons, right? And so how many inner shell electrons does iron have? Well, you know, all these,
Plus D.
well, you know, maybe the easiest thing to say is how many valence shell electrons does iron have? It has 2. N equals 4. Everything else is inner shell. And so it has 24 inner shell electrons. Z is 26. 26 minus 24 inner shell electrons shielding means Z effective is 2.
There's no.
There is no 2.
There's no 2.
What's this closest to? So it would be
1.
What is it closest to?
1.
1?
That's the closest answer. 28.
Did I say iron what? Iron plus or iron 1?
I'm not wrong.
Just iron? All right. The closest would be which one?
1.
1. Okay, that question sucks. So.
So we should say 2.
It wasn't meant to be that tricky.
So I think it would be 26 minus 24.
Yeah, because I put the obvious answer there, then I could have ridiculously won this far off, 1 versus 2 and then C, because everybody's going to say there's 18. And so people would say that Z effective is going to be 1, 2, 3, 4, 5, 6, 7, 8. Did I put 8 down?
Yeah. Yes.
So people will go, okay, 8, that's the correct one, right? But this was one of these psychologically screwed up questions. Where 1 doesn't sound right, and 8 seems to match, and therefore go with 8.
Well, like, if you just think about it, it will be larger than like 2.
So
Z effective usually is that large.
So Z effective would be the Z minus the valence electron.
No, Z minus the inner shell electrons. Yes.
More question.
Uh-huh.
Which MO below will be actually yield the greatest bonding interaction?
Which MO will yield the greatest bonding
Interaction.
Okay, which ones do you have? What are the choices?
Sigma 2s, sigma star 2s.
Sigma 2s versus sigma star 2s. Sigma 2s. Why is that?
Wait, what?
Sigma star is anti-bond. Yeah, it's
Oh,
Yeah.
what about sigma versus pi?
Well, it's the same thing with valence bond theory. What's better, a sigma or pi electron density?
Sigma.
Why is sigma better electron density than pi? Internuclear axis.
Yeah.
And so it's a sigma 2s is the answer.
Okay.
But we said this was in the,
What was the question?
which one's going to yield the strongest bonding interaction? Uh-huh.
Well, yeah,
What about sigma 2s versus sigma 2p?
Sigma 2s. Because,
It's not, it's just a question about
So you said, did you say that sigma 2s has the greatest?
It is the answer is zero.
yes.
What about sigma 2?
Oh, okay.
But why is it
Because
greater
the
than
answer is
sigma 2p?
symmetrical.
Because, one, what do you think is better overlap? Just using atomic orbital. A 2s overlap or a 2p overlap? As far as valence bond theory, which one should yield a stronger bond? The 2s or the 2p? Then since we're doing LCAL linear combination, all we're doing is, okay, we're adding this up, so this becomes a region of overlap here, but we still got electron density here and electron density out here. This is going to have most electron density in the middle. You know? Also, what would we expect, a sigma 2s or a sigma 2p? Sigma 2s. Although this is kind of funny. Okay. Because, these orbitals aren't to scale. I don't know why they don't put them to scale. There's, whoever did the graphics for this should have done it to scale. So they shrank some of them to get them to fit, so they all appear the same size. You see that? And, all right, what else? Go ahead, Matt.
I had a question on the other side of the resonance. If, say all the charges kind of came out the same, but over different atoms, but basically when you sum up all the charges, it was the same. But like one diagram has like 2 double bonds, and the other one has a triple bond and a single bond. Would those still be resonance, or?
Yes.
Okay.
Yeah. There's a certain thing when you ignore something because it's quite a bit less stable. It's this. Prop 65 warning. This agent, this might cause cancer or something, right? It's too much now. It's too much that you don't know what's really bad for you and what's not so bad, right?
You go put in your coffee or the big.
Yeah, Prop 65 warning. And so the situation is, do you treat everything bad, equally bad? But the same thing comes with this, because the Prop 65 is starting to lose its meaning, because it's everywhere, and you see it all, restaurant menus, whatever else. There's a Prop 65 warning. It's too much. And so the same thing, with resonance structures. And this is one we were looking at, and I talked about this, but some books will. Well, let me first show you a common error that I don't want to see. I see this all the time. Are these 2 resonance forms? No. Resonance, we just want to look at how the electrons are distributed within a molecule, not moving the atoms around. And so we always leave the atoms fixed in position. Right. So,
There you go. Each.
So this is kind of like the Prop 65 warning. Prop 65 warning, we want to make sure you get all of them in, right? All possible resonance forms in there, right? Actually, maybe this is not totally complete, but is there? Oh, yeah, maybe this is complete here. There's no other. But the problem with the Prop 65 is you don't know which one is kind of an insignificant hazard and which one is a significant hazard, right? And so this is something you got to know. And so, I wouldn't even bring this up, but I guess our book and other books bring this up. And when we come up with a resonance hybrid, yes, potentially some electron density can get spread out here, but when you look at this structure, how much is this going to contribute to the hybrid? We expect this particular structure to be a minimal or negligible contributor to the hybrid because, yeah, it's a lot less stable than those. What's the story here? What's the story that this structure tells you versus the other structures here? The oxygen lost an electron, but who did oxygen lose the electron to? Not carbon. To oxygen. So oxygen lost an electron to oxygen. Does that sound right? And how stable do you think that is?
Not stable.
Not stable. This can happen in an excited state, but it's not going to last for very long, right? And so this is why I said, just go ahead and ignore this. Now, some books are going to say, well, there's going to be a contribution, maybe 0.1% contribution to the overall hybrid. Should we? Yeah, it's true. There could be a little bit of contribution of this structure to the overall hybrid, but are we going to really worry about it? No. And so these are equivalent. And so most of the resonance forms we do are equivalent. And then when we generate the hybrid is based on equivalent resonance forms, right? And so that one's easily eliminated. But sometimes we do look at inequivalent resonance forms, and inequivalent resonance forms can offer a significant contribution to the hybrid. And we saw that. Where did we see that? N2O. We saw that with N2O.
That's an unequivalent resonance.
Yeah. I didn't talk about free radicals either. Free radicals have a single electron. So if you're going to put a single electron and not complete the octet, you can't complete the octet here because we can't go beyond 8. And so we could do something like this, where it comes close, 2, 4, 6, 7 electrons. If you're going to put a single electron, would you put the single electron and sacrifice oxygen's octet, or would you put the single electron and sacrifice the nitrogen's octet? Nitrogen because, yeah, nitrogen's less electronegative than oxygen. Well, what's the story here? Well, this is negative here. This is going to be negative here. All the other formal charges are 0. And so the story in this little structure is, okay, oxygen won the electron versus nitrogen. Well, which is better? Oxygen winning. But, you know, we have to compare. If there's a tug of war between oxygen and nitrogen, is there going to be any struggle, or is oxygen going to easily dominate that? There's going to be a considerable struggle because oxygen and nitrogen are the two of the 3 most electronegative elements on the periodic table. So here you have a good battle between oxygen and nitrogen, and it's not going to be a 100% winner take all, I think, right? It'll be more like an 80-20. Right, good. And so, yes, triple single versus 2 doubles can contribute, but this is a different kind of circumstance, you know, versus if we had something like this. Okay, here I have a triple and a single. I'm going to try to make a double and a double.
So now, how about this?
Can these 2 resonance forms contribute? No. Yeah, the carbon's messed up. Which carbon's messed up? Yeah, this one. Can carbon have an expanded octet? No. And so we have to look at it structure by structure to see. Boy. Okay, more questions?
Yeah, for the expanded octet, which ones can have the expanded octet again?
Okay, how about this? Which ones cannot have an expanded octet? Second period. Everything else can have an expanded octet. First and second period cannot have an expanded octet. Everything else can have an expanded octet. Any other questions? Well, today I was hoping to make good progress on not fall farther behind. But are there other questions?
We can move the final for Sunday. Sunday.
What chapters are going to cover for chapter 4? What section?
All right. This is what we have left to cover. We have properties of liquids. Properties of liquids would be like boiling point, melting point, or freezing point. Vapor pressure, we probably covered that before. Surface tension, I don't know if you covered surface tension yet. Viscosity. All those properties relate to intermolecular forces. The stronger the intermolecular forces, the more viscous, the higher the surface tension, the greater the boiling point, etc. And so we're going to look at intermolecular forces. Intermolecular forces aren't that many. You know, dispersion, dipole, and dispersion is also called London. So London, dipole, and hydrogen bonding. Those are those 3. Okay, then we're going to look at something called a phase diagram. Phase diagram, I don't know if you've seen. Let me give you a brief preview of the chapter. A little taste of the chapter to see what we have left. A phase diagram just tells us under what conditions, temperature and pressure, do we favor the solid, the liquid, or the gaseous phase. The border here is, you know, for example, this would be the melting point here. This would be the boiling point here. And so this is another representation of the typical phase diagram here. This is for ID. And so under what conditions, people use phase diagrams, what pressure, temperature, what is the favored phase that solves. And so we'll look at phase diagrams. And there's more than solid, liquid, and gas. There's also another phase called the supercritical fluid. And then there's another phase called the plasma. The supercritical fluids are interesting because supercritical fluids are a hybrid between a liquid and a gas. And so they kind of have the density of a liquid, but they expand to fill the volume like a gas. And so it has properties of both. And they're used, supercritical fluids are used for decaffeinating coffee. And they're trying to use these for washing machines. Your clothes would instantly dry in a supercritical fluid washing machine. But anyway, this shows multiple ice phases. Ice 1, ice 2, ice 3, ice 4. These are high pressure ice phases. All that happens is you tweak the structure a little bit. Makes it more dense. And so those are phase diagrams. What else are we looking at here? We're looking at crystal structures. We're going to do a lab on crystal structures next week. So I'll talk about crystals, the second part, or the second half of this chapter, on Tuesday next week, where we talk about network, covalent solids, and ionic solids. Network covalent solids would be like diamond, quartz. Ionic solids would be like salt, table salt. We also have one other, molecular solids. Molecular solids would be like ice, sugar crystals, that kind of stuff. So we'll talk about that Tuesday next week. And then in chapter 13, we're going to do a brief survey of chapter 13. Chapter 13, we talk about concentration, molarity, what else? Percent composition. What else is there? Have you heard of molality?
Yep.
Have you heard of normality? Normality we aren't going to really deal with, but molality we do because molarities are temperature dependent. The molarity of a solution changes with temperature because the volume expands and contracts with temperature. Molality is temperature independent. Molality won't change with temperature. And so molality is often used. But molarity is a heck of a lot easier to use. So all this talks about is what happens when you form a solution, you know? And so here's water. This is supposed to be sucrose, but sucrose doesn't form spherical molecules like that. Here, you can see the sugar dissolving. You see all the turbidity in there? Sugar is dissolving. And so we're going to look at the solution process. The solution process is you got to break the crystal apart, you got to break the water molecules apart, and then you got to make room. And this is called solvating a sugar. We talked about, as acid strength. Acid strength depends on three things: bond strength, polarity, and stability of the conjugate base. Stability of the conjugate base depends on charge delocalization based on inductive effect and resonance delocalization, and solvation or hydration of the solute particle. And so we'll talk about that briefly. We'll talk about, solubility and temperature, solubility and pressure. Solubility usually increases with temperature or decreases with temperature.
Increases?
Yeah, the sugar. More dissolves in hot water or cold water? In hot water. So you already got it. Okay. Gases. More CO2 dissolves in your soda at hot or cold? Cold. You got it. Vapor pressure of solutions, we'll talk a little bit about that. But these are called colligative properties: freezing point depression, boiling point elevation, non-electrolyte solutions. And so just some points about solutions. These are starting to go to suspension. A colloidal mixture is between a solution and a suspension. A solution, all the solute particles are dissolved. In colloidal mixtures, you have big particles that are suspended. And when you get a suspension, those big particles eventually settle. And so this is at the limit of a solution, colloidal solutions. Colloidal solutions, the big particles scatter light, so you can't really, they aren't totally transparent. And so what we're going to do is we're going to just hit some of the key points in chapter 13 and some of the key points in chapter 12 here in the remaining, in the remaining week. So the homework is going to be a very abbreviated homework assignment for this.
The homework will be chapter 12, 13, 2 chapters.
Chapter 12, 13, but it's not going to be your standard homework assignment.
What about 16? Do we have any homework for that?
Yeah, there's homework for 16. I guess I haven't posted that yet. I need to post it.
That's due on the final, right?
Yeah. That'd be good.
Can we do all of that before?
The grade for silver.
All of what? All of the homework?
Cover
Can we do all of this? Yeah. We could do all of this.
We should do lecture on Monday, maybe Monday and Tuesday. And then
Yeah, Monday and Tuesday, we're going to do all of it.
So then Wednesday would be, you have the lab.
No, we have a lab Tuesday.
You're final Thursday.
And we have final Thursday.
We have the final on Thursday.
So what would be like the day for us, like to review?
Wednesday.
Wednesday will be the review day.
What's that?
Wednesday will be the review day for the final. 4 chapters.
Hmm?
And this thing.
Review what? It's not 4 chapters, it's 14 chapters.
There's a one.
No, the review day was supposed to be every week you're supposed to be reviewing your notes, right? And so it's just a simple.
Yeah.
I mean, the notes.
I'm thinking 5 finals.
5 finals. That's a lot. Yeah. The reviewing your notes doesn't take as long as reviewing the book, right? No. And then chapter 11 and 12.
It's going to be more concept kind of thing.
Yeah, you could do this all from the notes.
There are calculations in those chapters.
There are.
There are calculations.
Yes. There are calculations. We're going to look at one of the calculations on Tuesday, but I was going to finish chapter 12 today. It wasn't that much stuff. But it looks like I'm not going to finish it because we're out of time. So
Shall we get started?
Yeah. I'll post the homework.
Never have.
The final homework set.
Those are